Okay. Now, before we go there, I guess according to your syllabus, your exam is on October 5th, right? October 5th. So you still have 2 weeks. So let's keep it as is, all right? Let's keep it as is.
Maybe October 6th. 5th is a Monday. Oh, wait, never mind.
Yeah, you're right. Well, it is a
Yeah,
Monday.
it's 5th. It's 5th. I thought it was Thursday today.
Foundation, yeah. Yeah, Monday's good. Monday good. October 5th. Let's keep it as is. Okay, I'll post the exam review as usual. All right. How you gonna do it? Again, same story. You'll have 5 minutes to download, maybe 1 hour to solve, then about maybe 10 minutes to submit. Right? Well, we'll post the instructions by the weekend or so. Okay, guys. All right, let's go back to that sand filter. Okay, let me share with you the last thing that we looked at. And it was, what is my stuff here? It hurts, I think. It's burning from the radiation. Okay, so we designed, this is one box. This is one filter, not two. It has 2 cells, okay? So this is the filter together, all of it, okay? This is one cell. This is another one here, second one, and the gullet between them, all right? Usually, okay, if you look at this from the top, let me try to do this. Okay, this is the gullet. And this is the second cell here, and it's like this, wow. And here is the depth, okay, the depth. And this is the gullet, runs all the way down, all right, until you get to the sand is somewhere here, right? Sand is filled here, sand. This is your filter, right? Beneath this, you have the gravel, right? Collection system and all that stuff, right? Now there is some kind of space here. Then somewhere here, you're gonna start installing your troughs, right, to collect. So they come like this here, right? They go all the way from this side and another one from this side, all right? Their task, this is from, you look from top view. They look like the following, actually. They like this shape, right? This shape, okay, troughs. So it looks like water enters from this side, dirty water. This is for backwash. And from this side, and it runs all the way and empties in the gullet, then it moves all the way down. You need another one from the other side here, okay? Recommendation, the loading from one side to each of one must be less than or equal to 1 meter. So 1 meter from this side, another 1 meter or less, all right? 1 meter from the other side, okay? This just gonna feed this one. Again, you have maybe 1 meter or less from this side, and here you have to install the second one, okay? And this has 1 meter from this side, and the other one has 1 meter from the other side, okay? So this gonna feed from 1 meter, and here 1 meter from the other side, and this is 1 meter. Okay. Now these distances 1, 2, 3, 4, 5, 6 must equal this number. Okay. In other words, you have the flexibility to figure out these distances between the troughs. Yeah. Okay. Based on the length of the filter box but you have the flexibility because the distance is less than or equal 1 meter. You can use 0.9, 0.8, 0.75, whatever. Okay, if you take 1 meter from here, it's not necessarily to be the same from the other side. All right, even though they prefer the same thing for each one. All right, kind of symmetrical loading, if you want. Okay, so once you finish with this, everything is fine. You're almost done. All right, you're almost done with the design of the filter box. All right, but not yet the media inside it. All right, the media inside it, mainly the sand. All right, the machinery, all machinery beyond our discussion. The sand, you need sieve analysis, right? You need sieve analysis. You need that cumulative curve, if you remember, right? Your sieve analysis. You calculate also all these kinds of the coefficients, uniformity coefficient and curvature coefficient, right? This is needed. Average diameter, right? We are not going to do that. This is very annoying, right? Very annoying. There are many things there with the sieve analysis for the sand filter. After that, you need to go and use Rose formula. Well, there are many formulas, but the most common one is Rose formula to calculate the head losses in it, all right? Your head losses should not exceed a certain number. If the head loss is going to exceed a certain number, okay, you need to stop the filtration and go ahead and backwash, all right? Backwash. Why is that? Well, the head loss gonna increase, right, as it is clogged, right? As clogging go more and more, head loss is gonna be more. Makes sense, right? So you achieve a situation where the head loss is gonna be some kind of indicator for you that clogging is not acceptable anymore. Okay, so some guys work with filters when they backwash it, clean it, using the head losses indicator, right? Some they just look at the water itself. Is it dirty now or is it clear? All right. Okay, troughs themselves, all right. Here are some, all right. Their length, you buy them actually, they are over the shelf, right? So travel distance less than 1 meter, be careful, this is very important. All right, you buy them. They don't manufacture them longer than that. Okay. For our example, if you look, this is 5.5. So look here, they took 1.1. All right, I would take 1. Maybe you work with these numbers down the road, right? And this is 101 here. Now, you always need one from this side and you need one from the other side, all right? Now, based on the remaining distance here, based on the remaining distance, you need to figure out how many you need to start in between, all right? In this case, it's 1, right? This is 1.1 and this is 1.6. Is that correct? And from this side, you have 1.1 and 1.6. How much is this?
Which one?
5.4. That's correct, guys. 5.4.
Yeah.
Yeah. Well, they are short a little bit. Well, this is actually maybe you can adjust this number, right? Just this is a rough, maybe rough estimate. But it's very close. Very good distribution, right? Very good distribution of the troughs. You need to distribute your troughs in that way as well, right? You need to know how many so you can order them. Okay. Now after that, we work with their size, all right? Their size. They sell them based on their width. See, this is cross section. This is the cross section of it. And based on the width, this is the standard. You tell them I need a width of, let's say, 30 centimeters. If you know that width, then from there you know that y here. See y? The straight dimension. This is your y. So if you decide on w, all right, and you decide on y, let's say 25, and w, they're gonna tell you how much flow rate inside it, right? How much water it can take, right? Then the rest is just, you know, this is W divided by 2, the radius, you know that. And the whole depth of it gonna be, this is W over 2 as well, right? Oh, please. So the total depth is Y plus W over 2. All right, sizing of the troughs. Now, once you know this, you can easily look here. I like this drawing, right? It explains. This is the gullet, remember, right? This is the sill here, right? This is your gullet going that way, gullet, right? Yeah. And this is your sill next to it, right here, the sill. I just did this before, right? This is the sill. This is the filter box. Oh, I'm sorry. I'm trying to do the filter box here, okay? So what we have here inside it, let's look at these numbers. All right, let's look at these numbers. This is the top of the trough. In other words, the 0.5 is a freeboard. Okay, this is the top of the trough. This is what we mean by that. This one here, the top. Here, the top of the trough. This is the bottom of it. This is the top of the sand. All right, here is the sand. This is your filter, by the way. Sand. All right, that's 0.4 is just between the top of the sand and the bottom of the filter itself. Gravel beneath it to support it, all right, and the drain, perforated pipes or blocks or whatever, right? The gullet ends at the end of the sand, right? In other words, everything else here, this is substructure, right, comes beneath the gullet and the filters together as well. Okay, makes sense here how you fill your filter box. Okay, now with backwash, this would expand because you are adding water from beneath with some pressurized air. This is clogged dirt. So when you backwash it, this should be able to rise all the way until it gets here and push it down here. Okay, now be careful. This is water here, water. Okay, water. So when you add water from beneath with pressurized air, you force these impurities to go up, right? You force them. So this layer of water gonna be dirty now. And it's the first thing that goes here. In other words, when you expand your bed, your sand should not get inside the trough. All right, this is why you have this kind of space, all right, of water. You cannot put the sand here. You're gonna go inside. You're gonna lose the filter. Okay, what you are going to discharge here with backwash is the dirty water, not the sand. So the sand expands to the bottom of the trough. All right, dirty water is the thing that gets inside the troughs, so it can be removed. from there. Now, when you finish, right, put the filter to its normal operation, and by gravity, larger particles gonna sit to the bottom, smaller ones to the top, smaller, smaller. Same thing with the sand, right? Larger to the bottom, smaller, smaller, smaller. In other words, gravity itself gonna take care of your filter. Don't worry about it. Okay, it's gonna sit back to its normal position. Okay, the backwash is very simple. Here it is, you know, just close all filters and open the flow from beneath, right? And allow it just to push up the, or expand the sand filter so the voids between them gonna become larger. And by doing that, the impurities would be able to escape under that force, okay? Under that force. Look at the video, you will understand what we are talking about, okay? Now, just quickly, I'm not going to stop here, all right? What kind of media you can use? See here the effective size, all right? Uniformity coefficients, you did this in soil mechanics kind of, you know, diameter 60 divided diameter 10. We know that one here, all right? And you use sand merely. This is the effective size of a particle desired for filters, right? Standard sieve, standard. Okay, there is an example here. If you would like, you can follow, but you need the sieve analysis. Here is the sieve analysis. Cumulative mass passing, you remember that? And sieve number, each has its own diameter, whatever. All right, this is the graph. Okay, it's the other way around. Your was, this is on Y and this is on X. It was flipped. This is why it looks strange here. All right, and this is not log. Well, it is actually. The size is log. This was your X-axis, I mean, and this was your Y-axis. Okay, and from here, once you know this, you can go ahead and calculate the head loss. And this is Rowe's formula, all right, for to calculate the head loss. Many things are needed. The most annoying part of it is this sum. Okay, in other words, you are going to do it in table form, right? Then you sum them up. Are you familiar with this? Yep, you should be. Drag coefficient, here it is inside the formula. You will need it. Okay. So based on this, you can use, here it is. This is how they do that. So they arrange everything in a table form, right? They calculate everything according. This is the sum here, as I said, right? You got these. These are what, this is what you have in Rowe's formula, right? In Rowe's formula, and you calculate the head loss. See, the head loss here is higher than the recommended. This means maybe you need to change what? Your sand in it. The sieve analysis gave you this number, right? Okay, guys, another thing that they calculate is how far the expansion of the bed gonna happen with the back wash, right? This D1 or DL, depth of expanded bed. You need to calculate that. So you know at least that from the top of the sand, from the top of the sand, you have enough space when it expands. This is the expansion, D1, right? And it will not go inside the trough itself. So you need to make sure how far you're gonna expand all the way to the top, right? So this is another thing that you calculate for your filter bed, all right? In addition to the design that we just talked about. Okay, so we're gonna stop only and make it enough for the design itself, all right? Figure out how many filter boxes you need, what are the dimensions of each filter box, all right? Divide it into 2 cells, figure out what's the length and the width of each cell, all right? And distribute inside the cell the troughs themselves. Good enough, all right? Okay, guys, if you don't have a question regarding the backwash, we can go ahead and talk a little bit about disinfection, contactors, contact basins, and how they design them. We are not going to talk much about disinfectants. You are familiar with this from last semester, all right? I mean the chemistry, all right? Let's talk more maybe about design of the basins and the tanks. Okay, guys, any questions so far? Are we doing good?
We good, thank you.
Yeah, we're good.
Okay, let's share the disinfection. Disinfection, let me see, where is my disinfection here? My disinfection. One, yeah. Okay, guys, so let's talk about disinfection. What we need. Okay, we need a little bit go back to the CT concept. Remember this, guys? CT concept from last time. I think you had a question or a problem actually in your test about it. You calculate the log inactivation. I give you concentration. This is the concentration of the disinfectant, okay? Let's say that's chlorine. Let's say that, all right? Okay. Disinfectant alone with its concentration is not enough to inactivate pathogens, microorganisms. You need a time of contact, all right? You need to leave it there for a given period of time so it's gonna work, all right? So otherwise, it will not, right? This is why with this coronavirus, and if you have some kind of disinfectant wipes, and they are not wet enough, all right, and you put it on and you try to disinfect, all right, it will not disinfect, and it will not kill it, in other words, when inactivate it, all right? It needs a time for contact, so it must be wet enough, so when you clean with it, all right, you feel that it's still wet there, so it needs time. It's gonna stay there for, you know, some seconds, right? I'm not sure how many for coronavirus. Nobody knows actually. So you need time. So this is the CT concept. All right. This was developed by the Environmental Protection Agency. And we have numbers for that. All right. They are listed in their tables for different kind of disinfectants All right, different kind of concentrations. So we're gonna use this concept, all right? You will see it down the road. It's in Wilson's formula for the inactivation. Remember log inactivation? Remember that?
Yeah.
It's written on the any disinfectant that you buy. It kills 99.9%, right? Well, this is log 3, I guess, right? This is log 3 inactivation. If you need more powerful one, you're gonna go with the 99.99, I guess. And this is log 4. Okay. So this is the one that is in the market that you buy. They tell you it kills 99.9 bacteria. All right. Based on this theory, you should know what does this mean, right? As an engineer. If somebody asks you, what does it mean 99.9? From where they get this number, right? From where they got this number? From here. Okay, this is how they got that number. Anyway, we'll go there, but most importantly, we are going to design the contactors because you need time, all right? So you need to put your water injected with a disinfectant, let's say chlorine, all right? And it must stay in that basin for a period of time. Well, it is a hydraulic detention time anyway, all right? But it should be long enough so it can, you inject it from here and it takes time until it gets out from here, which means you have enough time of contact. If you make it shorter, it will not have that enough or sufficient time of contact, right? These are very long ones, very long basins, tanks, right? So they design them in a different way, right, to save space. For example, instead of do it one run, they run it this way. Okay, forward, back, and forward. All right, so we're gonna run, the water gonna run all one. All right, you will see down the road what we mean. So this is what we are trying to do. Design these contactors, not contractors, right? Okay, you are familiar with this. I'm not going to repeat it. You did this in last semester. This is what you are going to kill. You need to inactivate. You are not going to kill, all right, all kinds of bacteria and so on in your water. Many of them are useful, okay? You are going to inactivate pathogens and mainly bacteria, viruses, protozoa, and amoebic cysts. All right, this is the indicator actually. If you have it in water, it's not acceptable, and if not, it's acceptable, right? Their concentration, in other words. So we do inactivation. Okay, what we use? Different kind of things, all right? Chlorine is the most used one, right? Cheap, okay, inexpensive in other words. Been around for a long period of time, all right? We know how to deal with it. Ozone, a new kind, relatively new. Okay, they use it in Europe. And UV radiation, RADS. These are more expensive. Okay, no new technology. You can use them if you have a small water treatment plant. That's not bad, all right? However, there is some disadvantage with those. Maybe you still remember from discussion last semester why chlorine is desirable.
Because it lingers around, right?
Yeah, something, right. it leaves residual chlorine in the pipelines after treatment. Okay, this is how when it reacts with different kind of organic material inside the water itself, right? And it leaves that residual. In other words, it's not enough when you finish with filtration. Here is your filtration. You finish with that. Now you bring water to the next step, which is the disinfectant. All right, disinfection here, D. All right. Well, water now is okay, clean and safe. All right, clean and safe. And this water goes to humans. All right. Many communities, they drink from there, right? They drink, they cook, they do everything well, clean and safe. Now, to take it from, this is the end of your water treatment plant. You're done here. This is the end of it, okay? This is the end. We finish all that stuff, all right? Before that, sedimentation, mixing, all that stuff. Now, to take it to a community, you need to run the water through pipes, pumping station, all right? Pipes. Here is your house. Well, don't think that if it's at the end of the water treatment plant, if it's safe, all right, with disinfectant, that you're gonna get it here safe. The problem is, along this journey, many things might happen, all right? Dirt, impurities might get inside these pipes, all right? That might happen, and it happens actually. This is what you have. So if you don't have disinfectant, right, throughout the pipelines distribution system, you might have a problem here, not safe. So chlorine is a good guy here because after you apply it inside the water treatment plant, it goes inside, all right, Cl2, it goes inside with water, Cl2, it becomes aqueous one. Now, it's gonna react with water. Any metal, any organic, any inorganic thing that is inside that water, and you have many of them, all right? So it's gonna react with these guys, react. Once you react with it, you're gonna lose some of that chlorine on these reactions, all right? This is what we call the reaction demand or chlorine demand. This is what they call. Okay, chlorine demand. Now the remaining is the one that you're going to use for disinfection. We call it the free chlorine now. Right? Gonna work for disinfection, right? Disinfection. In this place, all right? This comes in different forms, all right? Either as a compound form reacting with organic material, all right? And from there, you will get your chlorine residual, all right? After that, demand stuff. So the residual here is kind of, you still have chlorine in another forms, chemical forms, but still it is a disinfectant, all right? It is low in concentration if compared with this one. Yes, that's correct, but still it can do the job here throughout these pipelines, right? So this is why we like chlorine. It stays in the system, all right? And it's like safeguard, if you like this word. It's like a safeguard, right? Works like a safeguard. Chlorine residual that stays within the system itself. Okay? Ozone doesn't have that ability, and UV radiation also doesn't have that ability. Okay? I think this is why Environmental Protection Agency recommends if you use ozone or UV, you need to use some chlorine with it anyway. You cannot just use alone. That's because of this going here. All right. How you purchase it? Either gas, like here you see in these, or it comes as a liquid in a form of sodium hypochlorite, hypochlorite, or as a solid as calcium hypochlorite, right? Whatever is available. Okay. Dissolves with water. We are not going through chemistry. We are familiar with this from last semester. Okay. So this is the biggest advantage of chlorine, right? Residuals also stay there, right? Residuals. These guys don't have residuals. See, disadvantage for ozone. UV, same thing, disadvantage. No residual. Okay. Disinfection kinetics, Fick's law, Watson's law, Wilson or Watson? I thought it was Wilson, Watson. Okay, Watson's law. All right. The number of microorganisms after the number of microorganisms initial, right, and the change is through time with this coefficient K, right? All right. Now, after that, Watson introduced the concentration of that disinfectant. It's not like just KT, all right? All right. And from here, later on, this is time, concentration CT was taken by the Environmental Protection Agency to work with, all right? Okay. These laws actually they work with as you know population growth or population decay. Actually, this is negative here, right? So population decay. See the population decay here, negative KT. Okay. They assume that you can count them, right? This is the number of microorganisms in a given sample, for example, right? This is the death rate. Okay. Now, it's better to work with the CT concept than this concept, right? So if you know the concentration, your chlorine or any disinfectant, you know the time of contact, okay? You can go ahead and figure out what would be the log inactivation, right? So that's the contact time T10. Well, I'll talk about T10 later on, right? Let's go to the inactivation, log inactivation, right? Log inactivation equals KCT, right? So if you know CT from tables, you know the constant of inactivation K, you can find the log inactivation Li. And you did this last semester, and I remember you had a problem in the exam about it. I gave you K, I give you the concentration, I give you T, you calculated Li, right? Now, if Li is known, you can calculate percent removal or inactivation, right? Which is 100 minus the 100 divided by 10 raised to this Li. Okay, the 100 raised to that Li. This is parentheses. So if your Li equals 3, what would be the inactivation here? Let's do this math. Gonna be the 100 minus 100 over 1,000. That's correct? 10 raised to 3. So 100 minus 1/10. How much is that?
99.9.
Yep, thank you. This is 99.9. Okay. And this is actually mostly what you see around with disinfectants. So it looks like they use log 3. Okay. What does this mean that they use log 3? This equals 3, right? So it looks like they have some kind of concentration, all right, inactivation constant. Well, when they sell you something, it has some concentration. Now you wonder, what is T then? How these guys gonna tell that the log is equal to 3 and the percent removal is 99.9 if T is still variable? Is there anything written on these things tell us that you need to hold it there for a period of time? Maybe. Well, I believe that any disinfectant should stay there for a period of time. Otherwise, there is no meaning for CT concept. I don't have a disinfectant on me, but look at some of them. I believe maybe they write something as a recommendation. All right. Here you go. Everything was wrong. This is a disinfectant. Can you see this?
Yes.
Yep.
And it says here how much it kills. 99. See on the top?
Yep.
Is that a 3 log?
Yes.
Let me go back here and you will be surprised because you never read this. And it tells you, keep it on the surface for 4 minutes.
It says
Okay.
15 seconds on the back.
Where is it?
What we're looking at says kills 99.9% of bacteria in 15 seconds.
What is it?
Flip it.
And viruses.
Look behind it.
This one?
It says kills 99.
Oh, okay, here.
It's in bold. Yep.
Right. See? But the recommendation says keep it wet for 4 minutes. All right, here, I read this is here somewhere. In other words, whatever is that thing, T must be there. Otherwise, no meaning for CT concept. All right? In other words, with a given concentration, with a given constant of inactivation, you need a period of time for that disinfectant with this concentration to be able to inactivate it. All right? So be careful when you work with these, with this virus. All right? Keep it just wet for a little bit. All right? Just maybe a few seconds. That's good enough. All right? Okay, now we know this very well. Recommendations on what log you're gonna use, it depends. All right, there are many recommendations here are for Giardia cyst. This is our indication of how infected the water is. All right, we go with that Giardia cyst. All right, we use 3 log for it. Okay. So let's go to the design. If you have no question. Any question about disinfection, chlorine, ozone, UV? Some guys install UV at home for their, personal use. Who has a UV, small ones, like come with black filters? They have UV inside there. No? Okay. All right. Look, all these pictures are contactors, not contractors. And if you look at them, they look like serpentine, like snakes. They move, water moves. And you wonder why. Look, different shapes, right? This is kind of circular one, right? This water moves from the inlet to the outlet over this long path, right? As I said, it needs long tank, okay, long basin, all right? You don't have enough space. You need somehow to design it that can fit in a shorter space, all right? So this is a good idea to do it that way. See the long ones, how long are they? All right, these guys are lucky they have enough space. All that just to make sure that you have enough T. With your concentration, your CT is exactly what you need. Okay? If your giardicist is the indication, according to your local authorities, you need maybe log 3 for it. Right? So your CT should be able to give you that log 3. And it looks like you need time. All right? So when you design your contactor, right? When you design your contactor, the hydraulic detention time must be the one that gives you sufficient CT. Okay? And the most desirable one is this one, serpentine, all right? Water gets from some side, let's say from here. Yeah, it looks like from here. This is maybe the sedimentation tanks. This is maybe the filter. I don't see filter here. It's from here, goes all the way down, back there, comes here, goes back, comes here. And this is a basin here, right? Somewhere. So look how long it is, right? Serpentine chamber. This is what we are going to design, right? Serpentine chamber. Okay. Ideal. This is a plug flow, all right? Plug flow like a train, okay? When a train moves, all right, all boxes or wagons of the train, they follow each other, right? Follow each other like train plug flow, right? Moving together, all right? They have, all of them have the same velocity. And they move in the same direction. This is very ideal situation. In reality, you don't have that. There are many things happen inside your basins, right? You prefer it to be plug flow, right? If you have a pipeline inside the pipe, well, pipes are very good example of ideal plug flow, right? Especially closed and under pressure. Water just moves, right? This particle and this particle have the same velocity and they move in the same direction, right? It's not that it's moving this way and this goes that way, or back up. Recircuiting, we call it, right? In open channels, this doesn't happen. There are many things, especially short circuiting, right? Short circuiting. Some water, for some reasons in these basins, right, gonna flow over that distance in a shorter period of time. It finds a shortcut. all right, it finds a shortcut. So this is why it is sometimes annoying, especially if your tea is very sensitive for this infection, all right? If it finds shortcut, short-circuiting that water, shortcut, short-circuiting, right? Shortcut. So T actual gonna be less than the T needed. And in this case, maybe you don't have sufficient disinfectant availability, right, or effectiveness. So we have to count for that. We have to account for that one, all right? They try to prevent this from happening by doing these channels very narrow and very long, right? To prevent these circuitings. Many things might happen, cause that to happen. So this is the length to width, right? More than 1240 to 1. See how narrow and long? And height to width, right? 1, 3. Now, to be able to account for shortcutting, they came up with a concept that they call T10. See T10 here? T10, right? This T10 accounts, this is time, all right? This is actual time, if you wish, all right? This is the actual or the effective contact time due to your, the flow in your basin contactor is not ideal plug flow. It's not ideal plug flow, right? So in other words, your actual time is not equal T actual, or effective T actual is not the same as T detention. Okay, detention time is a theoretical value that we get from the very definition of Q equals V over T. Always remember that. So in other words, this is a calculated theoretical one. It is nothing but T equals V divided by Q, all right? And this is known, this is your constant value, this is your flow rate, all right? Now it depends on the volume of the contactor itself, all right? This is gonna determine how much T is. However, the time inside that V might vary, all right? And there are many reasons for that, all right? Sometimes water, when it flows, it makes eddies somewhere at the corners, all right? Recircuiting, right? Some of it actually, especially when you have different in temperature, in winter time, let me look at this. See this? This happens a lot. Stratification, they call it, from the word strata, stratification, right? Winter time. Okay, let's see here what might happen. Let's say this is your tank, okay? And let's say that the water comes in and leaves, right? And it's filled with water. Winter time is cold. The surface is colder than the bottom. Do you agree with that? This is warmer, right? Warmer. And it happens in this case that this is gonna go that way, the warmer one, right? And the colder one moves that way. In other words, you have two waters, right? One of them has longer path and the other one has shorter path, right? This is short circuiting happens here with the colder one, all right? Now, to account for that, they came up with this idea T10. T10 is experimental. They put a tracer there and they figure out how much time 90% of the water in that unit gonna pass through the unit, right? This is why we call it T10, 90%, right? 10%, not doesn't pass, in other words, right? Delay, in other words, delay. And they use what they call the buffer ratio, I guess they call it PR maybe, all right? Equals T10 over that T detention, okay? Based on T10 for that particular situation, right? Now, this depends on the design itself, this number, this ratio, depends on the design itself, okay? Let's look at them here. See, here is the ratio, okay? Baffling ratio. Depends on the design. In some design, this number is low. As you see here, very poor, right? See the design here, mixed flow, it's not plug flow, agitated, very low link with ratio, right? It's not very narrow and long like a pipe. We prefer to have a pipe. This is perfect, right? This is pipe. If your contactor gonna be a pipe, that would be perfect, all right? You inject the chlorine inside that pipe. And it's a long pipe, you're gonna calculate its length anyway, right? If you know the diameter of it, all right? However, some and most of them are the superior design here. See the superior design? Perforated inlet baffle, remember that? To slow down the water at the enter, like here is the basin starts, water gets in from here, and here you have baffle wall and perforated opening here. So it gets water gets inside it from this. All right. Serpentine, 0.9. All right. So it depends on the shape and the design of the baffle here inside the basin itself. So if you know which one you are going to design, in other words, your client tells you, listen, I need superior, all right? So you have to go with the superior design. Once you go with the superior design, you understand that your T10 divided by T detention time equals 0.7, all right? The only one thing that you need to be able to get detention time is to figure out this using the tracer recommendations, right? Tracer recommendation. This depends on CT, okay? In other words, this is a number that must be known for you to be able to do the design itself, right? Once you know this one, I think you are with me now that things get easier, right? If you know this number, then you calculate T, right? T equals that T10 divided by 0.7. Okay, you need time more than that T10, that the detention time, because this is short circuiting, right? Short circuiting. 10% didn't pass through it. Still there inside. This time is not enough, all right? And the rest of the story, detention time is known, Q is known. Okay, next, what you can find from here? Answers.
Volume.
Thank you, volume. Volume is known. Recommendations are given for these guys here. Recommendations. What you can do if the volume known, recommendation in length, width, depth. What you can do. Dimensions. All right. Use this recommendation and find the dimension. That's it. After that, okay, if it's long, then go ahead and find. See length to width here. You can use this curve if you want. Length to width ratio of the contractor depends on your T divided by T naught. If you are using superior, you can go from here and you can use this value. If you want. Oh, that's 0.6, sorry. I was thinking it should be 40. Here it is. Around 40. Length to width equals, right? Look at this one. This is very interesting. T naught over T equals 1. This means you have no short circuiting. You have a perfect ideal plug flow. But this happens when?
Big length.
Wow, look at that. That's a huge long pipe, right? Well, actually, you are not reaching that value. You're going to extend this, I don't know where. But at least 0.9 going to be close to 100. Okay. So in other words, this is ideal situation. You will never get that one, all right? All of them are, you will not do perfect. Okay, guys, now you know the rest of the story. Okay, go ahead, try to design this, please. Okay, Q is given, here it is, that's your Q. The required T10, see T10 is given here, all right? They decided to go with a CT equal to 100. This is what's required for inactivation in that area, in that place, in that water, all right? In that water. So the T10 is 100 minutes. So here they give, sorry, they give you T10, all right? Sometimes they give you that buffer ratio. Let's say 0.3 or 0.5 or whatever. And you understand that this is nothing but T10 over T detention. You are not given this one. You are given this one directly. And the client wants you to design a superior one. Okay. Go ahead, guys. Let me check who is here while you're working on this example. Go. Okay, let's go. Guys, be prepared. You know where is your name in the list. Eric.
Here.
Okay, Muhammad, Amir.
Here.
Ariola, Jan.
Here.
Ferdous,
Here.
Jalil,
Here.
Anna,
Here.
Kevin,
Here.
Osvaldo,
Here.
Elliot, Elias,
Here.
Kayla,
Here.
Alexis,
Here.
Jose Enrique,
Here.
Sammy,
Here.
Ismail, Ismail, okay, Esmeralda here,
Yeah, I'm here.
Brian,
I'm here.
Abdulaziz,
I'm here, Professor.
right. Justin,
I'm here.
okay, Yumara,
Here.
Maria,
Here.
Aisha,
Yeah.
Larry,
Did you say Larry?
Larry,
I mean, I'm here.
Robert, Robert not here? I saw him, no? Danny,
Here.
Vanessa,
I'm here.
all right. Javier Vergara,
Here.
Kevin,
Here.
and Kavinka.
I'm here.
Okay, guys, that's good. All right. Give me V. V equals. Answer, I need answers.
1825.4.
V equals, is it QT, guys?
Yeah.
Okay. You converted this, I think, because it's in minutes, or you converted minutes today, whatever you did, right?
Yep.
All right. So how much is a Q?
I got 1825.4 meters cubed.
18?
Yeah, 1825.4.
Yeah, it's also what I got. I know the solution says like 1853, but I don't know.
1825.4, that's meter cube per minute. Is that correct?
Meters. Oh, is that Q or V that you're?
No, I'm talking about Q.
Oh, Q is 18,400 meters cubed a day. So
Yeah, but you need to convert to minutes, no?
Yeah, you divide by 144, or no, it's 1440.
1440 divided by, okay,
Right,
that's
right.
good. All right, good. So you do that, all right? So this value, I'm not going to do it, you do it. 18400 divided by 140040.
1440, yeah.
Okay, now, what T you are going to take? The 100? This is detention, be careful.
I got 142.857 minutes.
Thank you. So your T10 over your T0, which is the detention time here, equals 0.7. All right? Now, this is the 100 goes here still. All right? So this is 100. Good. All right? And from here, you get T equals, yes, it's going to be 100 something. How much is it, Firdaus?
142.86.
Okay, let's 42. Okay, 86 minutes.
Yeah.
Okay, so this number goes here now. And from here you get the volume. And how much is it?
That one is 1825.4 meters cubed.
Oh, sorry. 18. Wow, what's going on here? 18 something.
Yeah, 1826.
Okay, 26. This is meter cube, right?
Yeah.
Okay, that's it then. You took what? What dimension you took for length and width? Length equals 40, you take it? Am I right?
Yeah, 40 and then 3.
It's arbitrary, right? Or no?
You can use another number, but this is
Right.
superior. Yeah, make
Okay.
it that way, superior. Otherwise, this will not apply. It's gonna go down maybe, all right? And what did you use for the height? Also 3W.
Yeah.
This makes it easier to work with the W alone, all right? So this volume now, 18, 20, is this 6 you said? Gonna equal
Yes.
W, 3W, 40W. Is that correct? And from here you solve for W, go back to L, go back to H. Right?
Yeah, W becomes 2.477, which you just round up to 2.5.
Okay, thank you. Length. How much is
L
your length?
becomes 99.11, which is about 100.
100. Your depth or height?
And H is 7.433, which is about 7.5.
Okay, thank you. Okay, now maybe this is too long, okay? And once we are with serpentine 1, okay, make it three loops, 3 lines. Go, come back, and you have to go again. Be careful. This is the direction going from the inlet to the outlet. All right, so you do forward, backward. Again, you have to go forward. Forward, backward, forward. 3, or forward, backward, forward, backward, forward. Okay, depends how long is it. Maybe you will have enough space, no problem about it. Do it a straight line, all right? But in this case, okay, in this case, it's a good idea to do it 3 as you see in this situation, all right? Each of it is 2.5, as you said, 100 the total, divide by 3, so it's gonna be 33.3. So what I get from here, all the way, all right, 33.3 meters, makes a U-turn and comes back again, another 33.3, then from here moves, go ahead, out, all right? That's a total of 100 meters, all right? By doing that, the detention time inside this one was 142 minutes. It took 142 minutes for a drop of water to get from the beginning to the end, all right? And there is a disinfectant inside. In other case, you satisfy the CT, all right, according to the numbers that you have. Okay, guys, that's it. Let's stop here, all right? I have another class back to back, so let me stop sharing and end this and enjoy the rest of your day, guys.
See you next week. Dr.
See
Thank you,
you.
Professor. See you
Take
next week.
care. Bye.
Thanks,
See you,
Professor.
Professor. You too.